Hey everyone, in this video lesson, we are learning how to break a vector down into rectangular or orthogonal or perpendicular components. This will be the last lesson in our unit on geometric vectors. So let's get started. As you might have heard me mention, when we break a vector down into components, we sometimes call these orthogonal or rectangular components because they're perpendicular to one another. Any vector can be broken down into these components. So for example, here's a vector I've drawn on the side here. You can take any vector and break it down into a vector that's, say, horizontal and vertical, or like east-west, north-south. If it's an inclined plane, into the plane, out of the plane. There's many different applications where you might want to do this. And normally, like 99.9% of the time, we're interested in breaking a vector down into components that are perpendicular to each other. So usually it's horizontal, vertical, or like north, south, east, west. There's sometimes situations where it might not be horizontal or vertical. We'll see like an inclined plane problem, but always interested in making those components perpendicular to each other. In one-dimensional space, like there's not really a point to this because one dimensions is like a line, and you can't really, here's a vector on a line. There's only one dimension. There's nothing to resolve into components there. The visual I have on the right here, that is a two-dimensional vector. You can resolve three-dimensional vectors into like an x, y, and then a z component as well. And then you can go farther and talk about n dimensions, which we don't in this course. Actually, we're going to stick, when we talk about components, we're going to stick to just working with vectors in two dimensions. So you have this visual on your lesson sheet. So this has some symbols we might use. So here you have a vector v, and that vector is described by an angle it makes, in this case with the positive x-axis. The size of that vector would be the magnitude of vector v. As you can see, I've broken it down into a horizontal component. So I call that v with a subscript x. And a vertical component, I call that v with a subscript y. And just using some simple trigonometry like SOHCAHTOA, because vx is adjacent to the angle theta, you would get its magnitude using cosine, and it's just hypotenuse times cosine theta. So magnitude of v times cosine theta. And in a similar way, that's the adjacent side. So that's where the cosine comes from. Vy is the opposite side. So you would use sine to get that value, and it would be the magnitude of v times sine theta. You don't have to denote angles from the positive x-axis. We've seen in some applications, like with true bearings. You might be given, I'll just use the Greek letter alpha there. You might be given a vector from that has a direction from north or from the vertical. And in that case, you can still resolve it into components. You might just resolve it into your vy vector that way, your vx vector that way. And then in that case, the size of vx, this should say the size of vx and the size of vy. In that case, the size of vx would be equal to the size of v times the cosine, times the sine of alpha, because in that case, the horizontal component is opposite. That's worth erasing to fix up. Yeah, vx would be sine alpha. So it just depends on what angle you're talking about, but you get the same components either way. And then the size of vy would be v times the cosine of alpha. So just be mindful of that. And then to get the size of your vector would just be the magnitude, would just be using Pythagorean theorem with the size of the components. And Pythagorean theorem works because we're resolving these vectors into horizontal, vertical, X and Y, and they'll always be at a right angle to each other. So let's just do a couple of simple examples here. So a tow truck is pulling a car from a ditch. I'm not a great artist, but most of us have seen a tow truck has its like hook up here or whatever. I don't know, but the cable pulling the car to the ditch, it's not pulling left, it's not pulling up, it's like pulling, in this case, it's like left and up, right? So we'll be able to resolve this into a component, horizontal component and a vertical one. So why don't you try drawing a diagram of this and then show that resolution of the force into rectangular components. So basically draw the force, and maybe and just draw a right angle triangle of the horizontal component, vertical component. Just give it a try. If you don't get it, that's okay. You can erase, but just give it a shot on your own. And when you're ready, maybe pause the video, try the diagram, and when you're ready, you can unpause and see how you did. And I'm going to show the diagram here. So here you have a force of 15,000 newtons, in this case up and left, but 40 degrees to the horizontal. So if you drew yours going up and right, it doesn't matter. It's the same math. And then determine the magnitudes of these horizontal and vertical components of force. And you notice just different subscripts, like it doesn't matter if you use Fy and Fx, it means the same thing. Here we have vertical, horizontal. So we've got A for B for the horizontal component, just using trigonometry, that's going to be the 15,000, the hypotenuse, times the cosine of the adjacent angle, which is 40 degrees. So 15,000 times cos 40, and the magnitude of the vertical component would be 15,000 times sine 40. So not too bad. And so I'll just calculate those right now. 15,000 cos 40. I might just go to the nearest Newton here. So that's about 11,491 newtons. And 15,000 sine 40, about 9,642 newtons. That's it. So the math is just a grade 10 SOHCAHTOA math, but any vector you can resolve into components like that. Let's look at a second example. Maybe you guys can try this one independently. So I'm sure we've all pulled a sleigh along the ground. When we're pulling that, we're not actually pulling it purely horizontally, because we're all relative a lot higher off the ground than the sled is. When we pull, there's a component pulling it forward, but there's just definitely a component lifting it upward, right? So I've asked you in this question to just resolve that 50 Newton force into orthogonal components. So a force, in this case, horizontal and vertical. So if you'd like to pause the video to try that, unpause when you're ready. If you want to follow along right now, it's a lot like the last question. So here we have our 50 Newton force. Again, orthogonal just means rectangular or perpendicular. So we want to make that into a horizontal force and a vertical force. So a horizontal force that pulls it forward, and a vertical force that kind of lifts it up a little bit and kind of reduces its apparent weight and how it feels. In this case, we're given the angle again with the horizontal, but if you had the angle with the horizontal, then you would know the angle with the vertical would be 60, and you could use 60 for the math as well, whatever you want. But yeah, if it's with the horizontal, we've just got 50 times cosine 30. With the vertical, 50 times sine 30. And we're done. So 43.3 newtons, pulling it forward. 50 sine 30. 25 newtons, pulling it upwards. So we've done 2 examples now. We're resolving a vector into its components. So the reason this can be helpful is, say you wanted to add multiple forces, or if you're doing taking grade 12 physics and learning about collisions, say you have 2 things colliding and they're traveling at, kind of not perfectly up, down, or left, right directions, and even like a third and a fourth vector, and you wanted to add all those together. So with our current skills, we would take these vectors and lay them out tip to tail, and then have to use trigonometry and somehow, find this length, and then in this new triangle, find this length, and in this final triangle, it becomes very, very challenging and time consuming and not very efficient. But if we resolve these vectors into their horizontal and vertical components, we can add up all those horizontal and vertical components together, the horizontal with the horizontal, because those are easy to add. They either add to each other or subtract from each other. And then we can recombine them at the end to get one resultant vector. So, and this would be an easy. You could program a computer to do this and and make it really efficient. So we're going to do an example here. So I've asked you to find the resultant force for 3 vectors by using components. So we're not going to draw a diagram and use trigonometry. We're going to use components. So you have a 60 Newton force that's north. So note that that one already basically is in components for you. You've got a north-south component of 60 newtons north, and your east-west component is just 0 newtons. But the other 2, you'll have to draw out and resolve into components. So I've given you a bit of a table here, so I can help you with the first one at least. So we've got this 60 Newton force, and I'm going to use this notation. So for east-west, and this is our first force, F1. I'll say that F1x, and I'll just leave it as a subscript. I won't have any vector symbol for now, but you could say F1x is 0 newtons because there's no east-west component. In fact, it's all north, right? You can say F1y is 60 newtons. And I won't use a vector symbol. Maybe I'll just assume that up is positive, so north, and east is positive to the right. The next one, if we draw this out, north 40 degrees east. So from north, 40 degrees east, here's our F2. Now we know we can resolve this into a component, and this is where I'll kind of let you try it. So I'll call it F2x. Excuse me, that's in the y direction. F2y and F2x, and you have this angle being 40, and it's a right angle triangle, and you have the size of F2. So can you calculate F2x? Can you calculate F2y? And then can you do that with the third vector, resolve it into a component? And if you want to try that, pause the video, give it a go. And when you're ready, I actually have this question kind of pre-done. So if you'd like to try it yourself, I definitely would encourage you to try it yourself. But I'm going to flash up the solutions to this part of the question right now. So as you can see, the east-west is 0, and I've actually included the directions just to help me keep track. So 60 newtons north. For the second guy, I got using sine because remember, it depends on where the angle is. Here the angle is with north-south, right? So the east-west component is opposite the 40 degrees. So we would use sine. I got about 58 newtons to the east, and this north component, 90 cos 40, about 69 newtons north. And then our 50 Newton guy is 80 degrees west of north. And then so for the east-west, 50 sine 80. For the north-south, 50 cosine 80, about 49 newtons, about 8.7 newtons. Now those east-west components are easy to add up, right? So 0 newtons and adding a 58 Newton force with a 49 Newton force. If one's going east, you can see the east one is a lot bigger, right? And the west one is smaller. So it's going to kind of subtract off. If you subtract those two guys, or imagine doing 50, if we chose east to be positive and north to be positive, we'd have, positive 57.9 plus negative 49.2. So whichever way you select, so like I said, the net force in the x direction is going to be to the east, and it's 8.7 newtons. And then we can add up the north-south components. In fact, all of these components have a north component. So when you just add these up, those are east. Remember, these are all north, right? So they're just all in a straight line. So we can just add these together, right? That's the nice thing about breaking it into components. Got about 137.6 newtons. So now you guys know that we have whatever our resultant force is, its x component is east and its y component is north. So something like this. I can find my cursor. There it is. We've got a component of our resultant north, and then a component to the east. And you guys are interested in finding what's the resultant, right? Just draw it like that. So looking back, you guys know this east component is 8.7 newtons. And this north component is 137.6 newtons. So for the resultant, you guys have practiced this, right? So for the resultant, we want to know the magnitude. So you can use Pythagorean theorem. And we want to know the direction. You can use the tan ratio. And so you'll be able to say that, that when you add those three forces, you're going to get so many newtons in a direction from north, so many degrees to the east. And so I'll leave it with you guys to do those calculations, and then you can pause the video, try that. And when you're ready to go, you can unpause it because I have this one done already. So here we go. When you add those guys together, you get a resultant that is 137.9 newtons using Pythagorean theorem, and the angle east of north is 3.6 degrees. So hopefully you got that too. But this can be more efficient than trying to draw 3 vectors and use trigonometry. It especially that would be really difficult with many vectors. But this process can be streamlined and made efficient. And again, this is something you could program a computer to do. All right, the last example we're going to talk about is a question where we're not going to be interested in resolving a vector into horizontal and vertical components, or north, south, east, west. In this case, we're going to take a vector that's already vertical and actually resolve that into orthogonal components. So like an inclined plane here. So this is the problem we're going to do in a second. So we have a box that's at rest, and it has a weight of 140 newtons. So that weight's dragging it down. So we're going to resolve actually that weight force, that gravity force, into a component down the ramp and excuse me, into the ramp. So let's do that over here. There. All right, so I'm going to get a different color than blue so it stands out here. Maybe green. All right, so you also see some other vectors on here too. If you think about what's keeping the box at rest, right? The box, like gravity is going to kind of pull it down the ramp. What keeps the box from moving? It's friction, right? So in this case, this diagram has indicated that little f, there's a little frictional force keeping it on the ramp. And what's preventing the block from actually just going down and kind of getting sucked into the ramp? Well, the ramp is pushing back on the block. And this is what people have taken physics will call the normal force. So what you guys have here, it's not quite, for people taking physics, it's not quite a free body diagram, but it is a diagram showing all the forces acting on the box. And these are all the forces right now. You've got gravity pulling it down. you've got friction holding it up the ramp, and you got the normal force preventing it from kind of like, falling down into the ramp. We're going to take this gravity force and resolve it into components. We're going to resolve it into a component down the ramp and into the ramp. So this takes some getting used to for people. Why are we resolving this into components? It's already vertical. But it will help us analyze because finding this component down the ramp will correspond with the friction force. Finding the component into the ramp will correspond with the normal force. For this question, I'm going to choose down the ramp and out of the ramp being positive. And our goal is to, I'm going to call this Fx, and I'm going to call this component Fy. So our goal is to find those components. Now, right now, in this triangle with the dashed lines, Fx, Fy, I don't have any angles. I know it's a right angle triangle, but we do need to find an angle. And here's how we can do it. The angle of inclination of the ramp is 20 degrees. So if you, I'm going to add too much color to this diagram, make it too stimulating. But where's my cursor? There it is. So if I just outline this triangle right here, it's a right angle triangle. That's a right angle. And if that angle is 20 degrees, then this angle up here is 70 degrees. That's actually the angle in our triangle Fx, Fy, and the 140 Newton force. The angle up in the top is 70 degrees, which makes the angle at the bottom here 20 degrees. So to find our horizontal component of gravity down the ramp, we'll use the 140 newtons, but we can see we're opposite from the 20 degrees, so that we'll use sine. So we'll switch back to a color that shows up better on the white here. So let's find Fx. So here, Fx is going to be 140 times the sine of 20. And so if the angle of inclination for this ramp changed, like say it was made to be 10 degrees, then we would just do 140 sine 10. That's always the case resolving gravity on an inclined plane into components. The component down the ramp will always be the sine of the angle of inclination. So I got about 47.9 newtons. And then Fy is 140 cos 20. About 131.6 newtons. So what I kind of teased earlier is, this box is at rest, which means that horizontal component that we found, 47.9 down the ramp, if the box is at rest, that means we know the force of friction as well, right? This indicates that the force of friction, at least its magnitude, is 47.9 newtons. So essentially we found the force of friction. And we found the normal force too, because that box is at rest. It's not going down into the ramp. It is not flying off the ramp. So we found the size of the normal force too. It's 131.6 newtons as well. So that's the reason why we resolved gravity to those components, because it actually helps us find those magnitudes. And then those of you who've taken physics would know that you could actually find the coefficient of friction. Some surfaces are very slippery that have a coefficient near 0. Others have coefficients near 1. Some have coefficients just above 1. But the coefficient of friction is the ratio of the friction force to that normal force. And so if you wanted to, in this case, you could calculate that. That should be the magnitudes. 47.9 over 131.6. Looks like about 0.3. I'll just do it since I started it. Wasn't planning to do that. Just got off on a tangent there. So yeah, the coefficient of friction on this ramp is about 0.36. That's for people who have taken some physics. So what should you guys be able to do after today? Take any force and resolve it into perpendicular components. You guys should be able to solve a problem given multiple vectors pointing off in various directions. You should be able to resolve them into components, add those components together, and then recombine to get a resultant. So much like this question here with the multiple vectors. You guys should also be able to resolve vectors into components that you might not necessarily be horizontal, vertical, or north, south, east, west, like the inclined plane problem. So next steps, the usual. I've posted some practice on the on the classroom or Brightspace with video solutions as well. That actually is the last video lesson of this unit before we get into algebraic vectors. So yeah, give these a try. As usual, let me know if you need any help. We'll see you guys soon.